So we've talked about how the first derivative can help us determine local mins and local maxes, increasing and decreasing. The second derivative also is useful when we start sketching graphs. So we're going to talk about the second derivative in this video and how it can tell us whether we are concave up or concave down. So definition, the graph of a function f of x is concave up on an open interval if f prime is increasing on I. Let's look at this picture here first. This curve is concave up over the entire graph, over the entire domain. One thing that helps students is to think concave up is shaped like a cup. So you can see here this curve, it looks like it could hold water like a cup. But I want you to look at the graph of the slopes that are around it. So here they've graphed some tangent lines and they've continued tangent lines on the other side. Remember, the tangent lines have a slope, and that slope is determined by the first derivative. These slopes, as we go down the curve, notice how they start to flatten out. At the bottom, they actually become zero. But everything on the left, these are all negative slopes. They approach zero, and then they increase to positive slopes. These slopes are increasing, okay, which means f prime is increasing. If f prime is increasing, then that means that your second derivative is going to be positive. So concave up, we're going to use the second derivative being positive to show us that that's what's happening. So you're not going to have a picture to start with, you're going to have the function. So find where your second derivative is positive and you're concave up. Over here in this picture, you can see that we have a section which is concave down. So students find it easy to remember down like a frown. So a frown is concave down, a cup is concave up. So hopefully that helps you a little bit. But notice it doesn't have a full frown, it just has half a frown because at this point here, we switch concavity and we become concave up. And this is half of a cup. It's not a full cup, but if you continue this curvature, it would be a full cup. So when we talk about concavity, it doesn't have to be the full frown or the full cup. It could just be half of it. But again, look at these slopes. These slopes are positive, but they're flattening out towards zero. So because your slopes are positive approaching zero, that means the slopes are decreasing, which means your first derivative is decreasing, which means your second derivative is negative. Over here, these slopes are all positive, but they're becoming taller and taller and taller. So over here, your slope again is increasing, which means your first derivative is increasing, which means your second derivative is positive. All right, so we have a test for concavities right here. This is what I was just talking about. If your second derivative is positive, we are concave up. If your second derivative is negative, we are concave down. So the relationship I mentioned is actually stated right here. If f is increasing, then f prime is greater than 0. We've talked about that one. Now, I want you to just put a derivative mark on each of these functions, and you get this statement here. If the first derivative is increasing, then the second derivative is positive. So the relationship between the original function and the first derivative is exactly the same as the relationship between the first derivative and the second derivative. And if you continued on from the second to the third, from the third to the fourth, it would always be this statement. The previous derivative to the next derivative, or the previous function to its derivative, would always be as it's stated here. So this is very interesting how the derivatives are related to each other. And then how do we find the concavity of a function? Well, if the second derivative is positive, concave up. If the second derivative is negative, concave down. But how do we find where that happens? You don't want to check every x. You're going to look for what's called the points of inflection. The points of inflection is where the graph of a function has a tangent line and where the concavity changes is an inflection point. So it has to have a tangent line, has to have a point there, and it has to change concavity. That's a point of inflection. So look for where the second derivative is 0 or the second derivative fails to exist. This should sound very similar to finding critical points, but we're doing second derivative now. So we call these potential inflection points, or PIP. So the potential inflection points, or PIPs, occur when your second derivative is 0 or second derivative is undefined. So same rules as critical functions, but it's for second derivative. So let me give you an example. We want to determine the concavity and find the inflection points of this function. To do that, you need to find the second derivative. So let's start with the first derivative. So 3x squared minus 6x. The second derivative would be 6x minus 6. So to find your potential inflection points, you set this equal to 0, second derivative, looking for potential inflection points, pips, or undefined. Well, this function here is a straight line. Straight line is always defined, so we don't have to worry about the undefined. We just need to solve for where it's 0. So 6x, bring the 6 around, divide by 6, x equals 1. Now this is not necessarily an inflection point. This is potentially an inflection point. The easiest way I find to categorize whether a pip is an inflection point or not is to build a second derivative sign chart. So the second derivative sign chart is just like a first derivative sign chart. You put your potential inflection point on your number line, draw your vertical line up to mark. This is a potential. This is where the second derivative is 0. And then you test. Pick a point to the left, let's pick 0. And pick a point to the right, second derivative sign chart, so you plug it into the second derivative. You need the sign of the second derivative at each of those test points. So we're testing here. So second derivative, make sure you plug into the right one. So 0 minus 6, so that would be negative. 2 plug in, so that would be 12 minus 6, that would be positive. So we have a negative second derivative and a positive second derivative. Now remember, it's the second derivative. So if the second derivative is negative, what does that mean about our graph? Negative second derivative means you're concave down. So I draw the frown. So concave down. If the second derivative is positive, that means you're concave up, like a cup. Or you can write concave up. I like to draw the curve. It helps me when I come back to graphing it, to just visually catch it real quick. I don't have to interpret what concave down means. I remember it means a downward curve like a frown, or up like a cup. Okay, so what does that mean about 1? Well, we change concavity at the potential inflection point 1. Therefore, this is, in fact, an inflection point. An inflection point is where you change concavity. Now, the inflection point is at 1. So that's your x value. How would you find the corresponding y value? Go back to your original function. So f, the original function, at 1. So it's right here. So 1 minus 3 plus 2, or 0. That is where the inflection point lies. Right? So determine the concavity. We did that. Find the inflection points. We did that. Let's try another one. Determine the concavity and find the inflection points of this function. Okay, so to talk about concavity and inflection points, you need your second derivative. So first derivative, power down, 1 power less. So minus 3 over 3 would leave us with 2 over 3. Second derivative, power down, so that's 10 over 9, minus 3 over 3. So that leaves us with negative 1/3, which I'm going to rewrite with positive exponents. So x to the 1/3, or cube root if you'd rather. So 9 cube root of x. Okay, to talk about inflection points, you need to find the potentials. The potential inflection points occur when this is equal to 0 or undefined. We've talked about this before. When you have a fraction, the fraction is 0 when the top is 0, undefined when the bottom is 0. When will the top equal 0? Well, 10 can't change. 10 will always be 10, so this will never equal 0. On the bottom will equal 0 when the x equals 0. So this is your PIP, your potential inflection point. Take your potential inflection point and make a second derivative sign chart. Okay. So we have x is 0. We're going to test, point to the left and then point to the right. So maybe -1 and +1. Who do we plug that into? Remember, we're building a second derivative sign chart. We want the signs of our second derivative. Plug it into the second derivative. So if we plug, let's see, which one? This one works. So -1, the cube root of -1 is just -1 times 9. So positive 10, negative 9, that'll be a negative. If we plug a positive 1 into our second derivative, we end up with positive. So we have a negative on the left and a positive on the right. Which means what? When your second derivative is negative, that means that your function is concave down. When your second derivative is positive, you are concave up. So at 0, we have the inflection point, assuming that there actually is a point here. So in the previous problem, we found a point, so that was our inflection point. How do we find if there's a point? We need to find y. So y we find by going to the original function and plugging in our x value where our inflection point appears to be. So if we plug in 0, we get 0. So our inflection point is that x is 0, y is 0. There you go. So at this point, we change concavities. There's another one. Last one here. Determine the concavity and find the inflection points. Again, you have to find your second derivative. So first derivative will be 4x to the third. Second derivative will be 12x squared. Potential inflection points occur when this second derivative is 0 or undefined. Well, this is a polynomial, so he is never undefined. He is equal to 0, though, when x equals 0. So this is our potential inflection point. What do? Second derivative sign chart. All right, so we're going to put 0 on our number line. Test a point to the left, -1. Test a point to the right, +1. Remember to plug them into the derivative, the second derivative in this case, -1, and second derivative at +1. So now this is interesting. X is squared. Well, what's always going to happen to a number that's squared? He's positive. Times a positive, what does that mean about the second derivative? If x squared is always positive times a positive number, this is always going to give us a positive answer. We don't even have to plug in our x values because the function, the second derivative, is always positive. So we are concave up and we are concave up, but we don't change concavity. So 0 is not an inflection point. What is he? Well, second derivative doesn't tell us. He was potentially going to be one, but because we don't change concavity, he's not one. That's all we know. First derivative might tell us more information, but without actually doing the first derivative test, I wouldn't know. So we might do that later. Now caution, we need to be careful about interpreting functional behavior whenever first or second derivatives fail to exist at a point. So first or second derivative didn't fail here, but it failed back here. So we had an undefined second derivative at 0. So be careful when you categorize those. At those points where the second derivative or first derivative failed to exist, where it's undefined, the graph can have asymptotes, vertical tangent lines, corners, cusps, or various discontinuities. So you have to be careful when you are in these situations. Most often, we're going to run into asymptotes. So that's the one you're going to want to watch out for. But you could run into the others in other courses. I don't think we have any in this course. So those were my examples for doing the second derivative concavity categorization. I encourage you to practice, do your homework, and I'll see you in the next video.